In this segment, we're going to talk about dynamics. This is the first of 3 videos on the subject of dynamics, and it's topic 2.2 in the IB curriculum. And when we're talking about dynamics, we're really just addressing the study of forces. And so let's start by defining what a force is. We can simplify what forces are into it being simply a push or a pull that one object exerts on another. Now the method by which that force is exerted, that push or that pull is exerted, can vary depending on the type of force, but all forces are simply pushes or pulls. Forces are also vectors. That means that the direction matters. So when we start adding forces together, we're going to have to remember those vector addition rules that we talked about earlier. And force is measured in newtons. The Newton is named after Sir Isaac Newton, who developed the 3 laws of motion that we're going to talk about as we get through this unit. A Newton is actually a derived unit that is made up of a couple fundamental units, being kilograms times meters per second squared. Now, based on the units, you may get some idea of how we calculate force. Before we start talking about the specifics of Newton's laws, let's look at a couple of general types of forces that we're going to be dealing with this year. The first, and probably the most common in our lives, well, the first 3 really, the first of these is weight. And weight is simply the force of gravity acting on an object. In our case, it's the force of the earth pulling us down. And this force of gravity acts on all objects everywhere. And it's important to realize that this is different from the mass. The mass is the amount of matter that makes up an object's body, and it's measured in kilograms. The weight is the force of gravity acting on that mass. So, an easy example of this, if you were to become an astronaut, fly to the moon, without changing your size in any of the training, your mass here and on the moon would be the exact same. But because the moon is about 1/6 the size of the Earth, the force of gravity on the moon is about 1/6 that of the Earth, and so your weight on the moon is actually about 1/6 of what it is on the Earth. Mass is, of course, a scalar quantity, as we've mentioned before, and as I said earlier, weight is a vector. When we're talking about the force of gravity on the Earth, that weight, the direction of the vector is always towards the center of the Earth. And this is what we just mentioned. And let me just throw in here, so you have it, and we'll talk more about our equations a little bit later, but the equation for an object's weight, we're going to use a capital W to signify weight, or sometimes you'll see it as F with a subscript G, which stands for the force of gravity. But either way, it's an object's mass times the acceleration due to gravity, which on Earth is 9.81 meters per second. The next type of force is what we call tension, and tension is simply force in a string. It can also be a chain or a cable or anything like that. Anything that ties 2 objects together, we can have a tension force. And when we use tension forces, when we talk about tension forces, there's really 2 forces involved. And those forces occur at either end of that connecting object. There's the force that's being exerted on the rope. That force is being transmitted through the rope, and the rope or chain or cable is then exerting that exact same force on the object it's attached to. Because the rope is the thing that's transmitting the force, the direction of the force is always in the exact same direction as the rope, or it's in the same plane as the rope. Then we have the normal force, and this is another one of those forces that we experience every day without really thinking about it or maybe necessarily knowing about it. The normal force is a contact force, and it's a force that arises because 2 objects are pushing together or touching each other. When you stand on the earth or you stand on the floor, gravity pulls you down, exerting a force downward on you. But the floor keeps you from falling. The floor is essentially holding you up by exerting a force that's upward, that's acting or counteracting gravity. This force that keeps you from falling through the earth to the center is called the normal force. And it occurs anytime we have two surfaces in contact. And the normal force always acts perpendicular to the surface of contact. So if you're talking about the floor, it's acting straight up. If you're talking about something pushing against a wall, it's acting straight out from the wall. And if you're talking about something that's at an angle, the normal force is also then acting at some angle. So if we just kind of diagram this out really quickly, here's our floor. If you have a box sitting on it, the normal force is going to act straight up. There's our 90-degree angle. And you can see we're writing out normal force as F with a subscript N. If this is a flat, imagine it's flat, wall, and something pushes against it, our normal force is going to act straight out. Again, there's our 90-degree angle. And if we have some angle, some ramp or hill or whatever it happens to be, our normal force again is going to act out at a 90-degree angle from that surface. So we're going to look like that. Then we have friction. And friction also occurs anytime two surfaces touch each other, except unlike the normal force, friction acts parallel to the contact surface, and it always acts opposite the direction of motion. And this is why friction always takes energy away from systems. And we have two types of friction. We have what's called static friction, which occurs when there's no movement. So as you're sitting in your chair on the floor, your chair isn't sliding around, but there's still friction between the bottoms of the feet of your chair and the floor. It's what actually keeps you from sliding around. And then the other type is sliding friction. And sliding friction occurs anytime there's actual motion between those two objects that are in contact. It's why if you slide something across the floor, it eventually slows down and comes to a stop. Now, if we take a couple of these forces that we've just talked about and kind of put them all together, we can come up with a diagram that looks something like this. Here we have a box on a hill that's at an angle. And the three primary forces that are acting here, and if this were a free body diagram, we draw a little dot. We have the force of gravity, which is acting straight down. Notice that it doesn't matter what the angle is off the ramp, the force of gravity always acts straight down towards the center of the earth. And it's equal to mg. The blue arrow here is our normal force, which as we can see is acting at a 90-degree angle to the surface that it's on. And then we have the frictional force, which is this lowercase f here. And you can see that the line here, that's the arrow, and the line here, that's the ramp, are parallel. So the frictional force is acting up the ramp because we're assuming the box is sliding down the ramp if these are the only three things acting on it. So it's acting up the ramp parallel to the contact surface. And then one more force here is just drag. And drag we most commonly encounter as air resistance, but it's really just friction that occurs in a fluid. And so drag occurs anytime you have an object moving through a fluid. We see it as viscosity often, but in any case it's really just a frictional force. And then we have the buoyant force, which is an upward force. It's essentially the normal force of a fluid pushing up on an object. Anytime an object is in a fluid, you have this buoyant force. If the buoyant force is greater than the force of gravity, the object floats. If gravitational force is greater than the buoyant force, the object sinks. Now, the last thing before we start talking specifically about Newton's laws is how do we diagram forces? How do we analyze the forces acting on objects? And we do this by drawing what we call free body diagrams. And free body diagrams are ways that we simplify systems. And we often even simplify the term free body diagram by writing just FBD. So if you see FBD, that's what we're talking about. Okay, so here on the left, we have a picture of a box. It's still a fairly simple scenario, but we're going to get into ones where it's more complex. We have the force of gravity, the weight, pulling down on the box. We have the box pushing down on the ground. We have the normal force of the ground pushing up on the box. And we actually have the force of gravity of the box acting on the earth, pulling it up. We want to look at just the forces acting on the box itself. In this scenario, there's really only three. So we simplify our object down to a point. So you can see here on the other side where we have our free body diagram, and we've simplified our box to a point. And so it doesn't matter how good of an artist you are. You don't have to be. You just have to be able to draw a dot. If you can draw a dot and a straight line, or a fairly straight line, then you can draw free body diagrams. Now on the box we have two forces. We have the weight, the force of gravity acting down, and so we draw an arrow down to show that force. We draw an arrow acting up to show the normal force, the force of the floor pushing up on the box. And you'll notice in this case the arrows are pretty much the same length, and they should be the exact equal length, because just like any other vector, the length of the arrow indicates relative strength or relative size. And in this case, the normal force and the force of gravity are the same size, so their arrows should be the exact same length. And so anytime you have a free body diagram, you're going to start with a dot, and you're going to have your arrows coming out from it. Okay, so all of your arrows in a free body diagram should originate, the tail should originate at the dot and should point out from it in the direction of that force. Okay, so now let's get into the actual Newton's laws. We'll start with Newton's first law. Newton's first law deals with situations in which the forces are balanced. And it says that an object will either remain at rest or maintain a constant velocity until acted upon by an unbalanced force. And this is also known as the law of inertia. And inertia is another term that we're going to need to know. And inertia is the tendency of an object to resist change in motion. Tendency of an object to resist a change in its motion. And so this kind of goes along hand in hand with the law. If an object is at rest, it's going to try and stay at rest. If an object is in motion, it's going to try and maintain that motion. It wants to maintain a constant velocity. Now, whether that velocity is 0 or some non-zero number, it doesn't matter. It wants to maintain a constant velocity. So in its motion. Now, when the forces on an object are balanced, that means we have what's called a zero net force, and there's no acceleration. And if there's no acceleration, as we know from kinematics, when acceleration is 0, change in velocity is 0. So let's clarify this term net force to make sure you understand. The net force, or when we talk about the net anything, the net gain, the net income, the net whatever, is the total, in this case, force acting on an object. And so in order to get the net force, we have to add up all of the forces acting on that object. If that net force is 0, then the acceleration is 0 and the velocity is constant. And that's what Newton's first law says. And this results in what we call translational equilibrium. And if you kind of look at the term equilibrium, it means balance. And so it means everything is balanced. All the net forces cancel out. And this term translational is simply a term that we use to talk about linear motion. We have other terms like rotational, which we use when we're talking about something spinning. But translational refers to when something is moving along. It's moving in a line. So let's look at this net force a little bit more. And as we mentioned before, the forces are balanced or in equilibrium when the sum of all the forces in all the directions is 0. So we do have to kind of keep this in mind in a three-dimensional world that forces can act in any direction. When the net force is 0, the acceleration is 0, and so the velocity is constant. So all this is saying down here, these three little equations, this big kind of scary looking E is a sigma. And it's just a Greek letter, and it means the sum. So when the sum of the forces, and here we have the net, so when the net sum of the forces equals 0, that occurs when the sum of the forces in the x direction equals 0, and the sum of the forces in the y directions equals 0. Over here, our little picture of our balloon, we've got some forces acting on it. We've actually got 4. We have the weight of the balloon, which is obviously probably not very much. We also have, and you can see it's tied to a string, we have the force of tension in the string on the balloon. Those forces are both acting down. We also have a buoyant force on the balloon that's acting upwards. If we assume that this balloon isn't moving, it's just hanging there, it's just sitting there on its string, then it's not changing velocity, the velocity is staying at 0, which means that it's not accelerating, which means that there must be 0 net force, and so that tells us then that the weight plus the tension has to equal the buoyant force, so that those forces balance each other out. And so they're in opposite directions, they cancel each other out, so when the net force, and notice that when we're talking about net force, we actually write out net so that we don't confuse it with normal force. When the net force is equal to 0 newtons, then the acceleration is equal to 0 meters per second squared. And that's what